So what we're doing today, we have a homomorphism, and we have some subgroup over here in H. Well, what I'm going to prove is that over here in G, the inputs, I can find some subgroup of G that maps over to V. So that's what I'm going to prove today. So in particular, if H is a quotient group, then we can always find a subgroup of G that maps to it. In fact, we can say that there's some subgroup that contains N, but we're getting ahead of ourselves. So we're going to say U is equal to the inverse image, which would be exactly that. The inverse image is all the G that map into V. It's a subgroup. So, so V is a subgroup of the image, so that means something has to map to it, so it can't be empty. So it's non-empty, and then we just need to show, this is a single-step subgroup test. You could show that it's closed under inverses, and then it's closed as well, but this is just a single-step thing. So well, since A and B are in U, phi of A and phi of B are in V by definition of U, because U is just the inverse image. Well, since V is a subgroup, I have inverses in V. So phi of B has an inverse, and so I can say that phi of B inverse equals phi of B inverse, which belongs to V. Well, since phi of B inverse belongs to B, phi of AB is split it up. It's in V by closure. So that tells me that this must be in U, because it maps over into V. So that's good. That means it's a subgroup. And we're basically done. So note that the kernel is going to be contained in U. All right. So if you want to use this with quotient groups, you can do this too. You just look at the inverse image. Right? If G goes to G mod N, if you have some subgroup over here, that's basically going to go to an L mod N, where L is over here. It's all the things that map. Right. And maybe you have L1 up to NLM. That means that L over here will equal, basically, well, maybe I'll say the union of the NLI. You just kind of throw all these things together. So it contains N, and it contains some other stuff as well. All right, thanks.